Now let's share my screen. Okay. Everybody, can you see my screen?
Yes, Dr. Ali.
Yes,
Yes,
sir.
the message to you about the first midterm exam to be held on September 22. This
Okay.
means next week, coming week on Tuesday. And as a syllabus, as I mentioned, you have to look all class lectures, including Thursday. I mean, today's class and then next class that will be included. That is the meaning. Today is September 15th, so you have to consider the September 17th class as well. And then you have to look all numerical problems or questions that you have discussed in the classes. And then the total of 7 to 8 questions will be asked. And there will be some short questions and some numerical problems. That is the meaning of total 7 to 8 questions. And then I will be creating a Dropbox where you have to upload your answers, exam answers, in the PDF file format. So I will be allowing you about 3 hours. Like I will make the exam paper available on eCourseware at 5 p.m. And then right after that, you can start writing if you are available, or you start at 5:30 at the class time, but it will be available. You can see it on eCourseware. And
So
then
at what time it will be available, Dr. Ali?
at 5 p.m.
Oh, okay.
At 5 p.m. And then I will allow you until 8 p.m. like 3 hours. I think that will be fine, right?
I think the question would be very tough then.
Yes, sir.
No, that is not my
Yes,
intention. My intention is not that's why I am allowing 3 hours. I am allowing 3 hours so that like okay, before start of the exam, you all can properly open the file based on your internet system, and then after the exam you can scan and make the PDF file and then properly upload. That's why I'm allowing 3 hours. My intention is not to make the question harder. Yeah. It will be as usual standard question. So everybody, could you follow me what I said?
Yes, sir.
Yes, Dr.
Yes. Yeah. So therefore, we will be waiting exactly at 5 p.m. The question will be available on eCourseware. I will create a new tab like exams, and then there you can see like midterm exam one. And I will create a Dropbox as well, the way you submitted your homework nearby that midterm exam one. There you have to upload within 8 p.m. Yeah. Okay, and that is the scanned and PDF file. Okay, so moving forward, we were discussing, I think, this problem, but we were ran out of time in last class. Did you try this one? Or right now you can start. Right now you try it. See the problem, a 3-phase 600 MVA, 2-pole 60 Hz synchronous generator as shown in the following figure has a rated current of 160 kiloampere and feeds via a 1:2 transformer, a 3-phase 750 horsepower Y-connected induction motor that has a full load efficiency of 90% and a lagging power factor of 0.75. So, I mean, very long sentence. So this is the synchronous generator. It has 600 MVA and its rated current is 160 kiloampere. And it is powering an induction motor, 3-phase induction motor that has efficiency of 90% and its output rating is 750 horsepower. Now, this is the transformer, definitely 3-phase transformer. Turn ratio is 1 and 2. This means right side has, secondary side has 2 times more winding than the primary side. That is the meaning. Other informations are given. So, and then that motor has lagging power factor of 0.75, this motor. Now, to improve the power quality of such a load, a capacitor is connected at the load terminal, that ultimately makes the power factor of 0.85 lagging. Now here at this terminal, you connected a capacitor. So you all know that capacitor can raise the power factor. That capacitor made the power factor 0.85. So what is the value of reactive power provided by that capacitor? So definitely it is capacitor, it provided reactive power. What is the amount of that reactive power? And also, what should be the motor terminal voltage? What voltage is available here? What is the rated voltage at the motor terminal? RMS value, line voltage. So two questions. What should be the reactive power that will be provided by the capacitor with a view to improving the power factor 0.85? So everybody, do you get the clue how to do that? So therefore, at least you can understand, previously, I think 2 classes back, we were solving similar problems. I mean, not exactly the same, but similar problem of power factor improvement. So you can use that power triangle to solve this one, because the initial power factor was 0.75 and then later it was improved 0.85. So I am just taking you to that whiteboard and drawing a picture for you, and then you all will get. So you see, you all use this one. Yes. So you see, this is P, this is Q, and then this is theta. And then once capacitor was connected, so the Q value got reduced. So therefore, again, before you did, this was your original value. And this portion was provided by the capacitor. I mean, from here to here. And so therefore, this is the old value. And this portion is the new value. This is the new value. So therefore, definitely this is cos the theta old, and this is your new theta. So therefore, you have to find out this Q cap, how much reactive power is provided by the capacitor. So this means that you have to do Q cap equal to that Q old minus Q new. Just you have to do this thing. So everybody, then right now you try at your note, this one, you draw this picture and then see which thing is given and which things are not given. So this was the question. You have to just find out the reactive power amount, Q cap, which is this Q old, what was the old or the original reactive power, and what is the new reactive power. You just need to subtract. That will be your answer in var or kilovar or megavar, whatever. So everybody is fine. So the thing is that first you have to find out what is the P value here, active power. You can understand that Q will be changed because your theta is getting changed. I think original power factor was cos theta old was, I think, 0.75, right? It was 0.75. And then you are getting cos theta new, the changed or the improved on 0.85. So then what should be the P value? If you can know the P value, then you are done. So what should be the P value? You see the induction motor efficiency was given. I think induction motor efficiency was 90%. So what is the definition of efficiency? Efficiency is output
Output by input.
input. I think now you all got the clue. This is output over input. So this means that because in this look in this picture, this is your electrical power. This is not the shaft power, or this is not the mechanical power. Just keep in mind, this is the electrical power. So we are writing this efficiency equation for induction motor. So induction motors, this is output. So this output means this is definitely the shaft output. This output is at the shaft. So therefore, definitely you will not be taking that on. You have to calculate the input power, because this is that actually that P, input power to the motor. So this means input is output over efficiency, right? So from this equation, input is output over efficiency. Efficiency value is given. What was your output? I think some number was given, 750 or something horsepower. That value will go there, and you have to convert that horsepower into watt value, and then find out input. That input value, this will go here. So everybody, can you follow me?
Yes, Dr. Ali.
Yes. So everybody, please, right now you do in your note. Right now you do, and then you let me know the result. Another thing, I think you understand that we did similar things, I think 2 classes back, once we did this up. So the key is that efficiency, put the efficiency value and output power. So if you have drawn this picture, then I am going there, I think, to know that value. You see, yeah, that was the 750 horsepower. 750 horsepower. That is that number. So this means 750, it is written here, 750 horsepower is the induction motor output, but this is the shaft output, keep in mind. Because this is shaft output, that's why it is expressed in horsepower. If it is regular input power or electrical output power, definitely that will be expressed in terms of kilowatt or megawatt or simply the watt. So therefore, this is efficiency. You find out the input power which is going to that motor. That is your power in that power triangle. I think everybody got the hints and you are able to do. So everybody find out what should be the reactive power value that is being provided by the capacitor. So capacitor is connected here. Is everybody trying?
Yes, Dr. Ali.
Yes, please, everybody try. Sindhuja, are you online?
Yes, doctor.
Yeah. Could you follow me what I said?
Yes.
Yeah. Okay. So you remember we did on similar problem using this triangle before, but that day that P on the triangle x-axis value, P value was given, odd value. But today that P value is not given directly, but the motor information, motor input output given, as I told, 750 horsepower, and 1 horsepower is 746 watt. So you have to convert this horsepower into watt by multiplying 746. And this is your output, this is efficiency. You find out input. that input value will go for the P value on the power triangle.
So
On the-
is it 0.122 megabar?
No, it looks like
Q2 or the what is the value of reactive power provided by the capacitor?
reactive power capacitor. The answer should be 163 kilowatt. 163 kilowatt. That is the answer.
163 kilowatt. Okay, I
Yeah.
got different one. Let me
Yeah,
check.
yes. Please check from beginning. Somewhere there is some mistake. Okay, so everybody just see the answer. Answer will be 163 kilowatt. Yeah. Now you calculate and you match whether you are getting or not. Manoj, did you convert 750 horsepower into watt?
Yes, Dr. Ali, I just multiplied by 746.
Okay, okay, that's right. Then maybe somewhere in
So I got power equal to 0.622 megawatt.
0.622. Yeah, that's right. That's right. I mean, I
And,
expressed in kilowatt, 621.667 kilowatt. So you are right in megawatt. Yeah.
and I got Q1 equals to 0.411 megabar. If
You mean the answer?
no, the Q1,
Oh, yeah, Q old original value.
yes, how much you got?
Q old I got 548.26 kilowatt. So if you express in megawatt, then 0.55 megawatt.
Okay.
So maybe there is some difference there. Um, so cos theta old, I mean, previous power factor value is 0.75. And updated, this means improved power factor value is 0.85.
Yep.
Okay.
0.622 multiplied by 10, 41.4. Yeah, I got 0.548 megawatt Q old.
0.54 megawatt, yes, that's right. Now it is right.
And 0.703.
So now find out the Q new.
It's 0.386.
Yeah, megawatt, right? Yeah, that's
Yeah,
right. Then right, yes. Now you are in the right path. So therefore, see, finally you should be getting capacitor reactive power on about approximately on 63 kilowatt.
true.
Yes, or 0.163 megawatt.
Yeah, 162.
Yeah, okay, yeah. I just like I got on 62.99 something, so that I approximated on 63 kilowatt. Kamana, are you getting?
I'm calculating. That's
Okay,
all.
okay. Venkat,
Yeah, I got 162, sir. Kilowatt.
162
Sorry,
kilowatt.
megawatt.
Okay. Amani,
Yes, Dr. Ali.
so are you calculating?
Yes, Dr. Ali. I got 0.189 megawatt for Q capacity.
0.189.
Yes, sir.
It looks like wrong result. It should be 0.16. or 0.163 megawatt.
But I got for I was sharing my answer on the chat. Can you please open the chat because I got for PN 0.62.
Okay, just a moment on the
Take your
chat.
time.
Let me stop sharing. Chat. Hold on. PN 0.62. Yeah, that is right. Megawatt. And Q old. Hold on. 512. Oh, you got Q old something low. Q old should be 0.55 megawatt.
5.
Yeah, that is the wrong. Yeah, that's why your result wrong. And then the similarly Q new is, oh, your Q new is completely wrong. Q new is 0.385 megawatt. So therefore, see those two. I think there is some issue in your calculator tangent.
I changed my calculator.
Oh, yeah.
So
Oh,
let
then,
me share also the values for 10 old.
okay.
It's equal to 0.882.
10 theta volt 0.88, right?
Okay, 10
And 10 theta
new,
yes,
new it's equal
0.62.
0.62. Yes, I got this value. And BN is 0.62 mega.
Yeah. In input power, P in, right. P value is 0.62 megawatt. Yeah. So then now you calculate. So now you should be getting the correct result.
Oh, I got same result for Q old.
0.18.
For Q old, I got 0.529.
So you make sure that is your keyword. Look, keyword is 0.548 megawatt. Keyword 0.548 megawatt.
I will write down what I did. It's 0.6 equals 0.5292 mega. This is my Q old.
Keyword 0.53. Keyword mega. Yeah. So like we got 0.55 close by 0.55 mega. So why is it differing that much?
I don't know because this is the 10 value for the theta old and 0.0 it's the value for PN.
0.621.
Maybe that's why because I did 0.6.
Oh no. That's why. Yeah,
Okay.
you consider like I myself wrote like 621.667 kilowatt input. Yeah.
So that's maybe why.
That's how it is. I guess.
Okay.
Yeah. Please you consider after decimal 2 digit at least.
Okay, I'll do that right now.
Okay, keep going.
Thank you. 2.
Sindhuja, did you get QCAF 163 kilowatt approximately?
I got 160,
How much you said?
162.
Oh, okay, kilowatt, right? Yeah.
Yes.
Okay.
So I got 0.548. Is this value acceptable?
0.548 kilowatt, right? Kilowatt, right? Yeah. I mean megawatt.
Megabar, yeah.
Yeah. That is fine. That is kilowatt.
Okay.
And then Q new should be 0.385 megawatt. So therefore, those who are done, you got correctly that Q cap. You please answer the next one. What is the motor terminal voltage? So Manoj, Venkat, Kamana, you, Sindhuja, you start finding what is the motor terminal voltage.
Dr. Ali, I have 7,500 volts.
How much?
7,500.
7,500.
Yes.
It is wrong. Like I got 4.33 kV. 4.33 kV. Can you please check your calculation?
Yes, I will get check.
Okay. Manoj and Kamana, did you try the motor terminal voltage?
I'm working on it, Dr. Ali.
Okay, yeah. So everybody, the result should be 4.33 kV. So motor terminal voltage in this case, definitely it is the line voltage, line to line voltage, and not the phase voltage. Line to line voltage and RMS. Like I got 4.33 kV. So keep in mind on the transformer, there is turn ratio left side on, right side too. So therefore, definitely motor terminal voltage will be 2 times larger than the primary side voltage.
Dr. Ali, I got 4.33. That's the
kV,
line
right?
voltage. Yeah.
Yeah, kV, yeah, okay.
Bothman calculated the phase voltage. So if you divide by √3, then I mean, if you multiply it by,
Okay.
Yeah, that's what I did. Yes, you're right.
Yeah, right, Othman now? Yeah. So therefore we have to use S equal to √3 VLIL. So just a moment. So Sindhuja, for the next part, you need to use this one, S equal to √3 VLIL, this equation, where S is your MVA, S was 600 MVA. This is 600 MVA. And then IL value was given 160 kiloampere. It was 160 kiloampere. So therefore from there you are getting VL value. And that is the terminal voltage of the generator. And then there is transformer, so you have to multiply that value by 2. That will be your answer. So that should be 4.33 kV. Sindhuja, could you follow
Okay,
me?
Dr. Ali. Yes,
Yeah,
I'm done.
Use this one to calculate the motor terminal voltage, S equal to √3 VLIL. And S 600 MVA, IL 160 kiloampere. And then you'll be getting VL. Finally, you have to multiply by 2. Okay, so I am going there. Okay. So Venkat, did you get the same number?
No, sir, I'm trying.
Oh, okay. Kamana, did you get that Q capacitor on 63 kilovar?
Yes, Dr. And I got the final value 4.33.
kV? Yeah, okay, then fine. Okay. Amani, finally, did you get capacitor?
Yes, Dr. Ali, I got it.
Okay.
I got it, Dr.
Okay, and then now, Amani, now find out the motor terminal voltage.
I'm working on it.
Oh, okay.
So Dr. Ali, VC, it's equal 4.3 millivolt.
4.33 kilovolt.
Kilovolt.
Yeah.
Okay.
4.33 approximately. So first, you should be getting VL line voltage 2.17 kV. That is for the generator. You see at the terminal of the generator here on the primary side of the transformer. And then you see turn ratio, secondary side has 2 times of more turns. So you just need to multiply by 2. And we did not put any component, any line or any resistance reactance. So there is no drop. Directly the secondary of transformer appears as the motor terminal. So it should be 4.33 kV.
I don't know why I got the correct number, but it got it milli, not kilo.
Maybe your even new calculator is not helping you.
I have to make sure to get a good calculator before to use the homework. I'm sorry, to use the test.
Before buying, you need to solve a problem at the store and then you have to bring it at home.
Yeah.
Venkat, did you get?
Yeah, I'm getting 0.42 millivolts.
Milli?
Yeah.
So 160, you see 160 is kilo ampere.
Yes.
And then 600 MVA. So VL value should be 2.17 kV. VL, and then motor terminal just 2 times of that.
So Dr. Ali, to get the result, I have to divide 600 over square root for 3 times 160 kilo, right?
Yeah.
So that's why I got milli.
Okay, so therefore your numerator should be 600 multiplied by 10 to the power 6 if you convert MVA into volt ampere. And in the denominator, root 3 multiplied by 160 multiplied by 10 to the power 3. So the numerator 600 means 600 multiplied by 10 to the power 6.
Sorry, Dr. Ali, but I did not get that. Can you write it down, please, for me?
Oh, okay.
I'm sorry.
No, that's fine. Hold on. So just a moment. Okay, so like this is the equation, right? Yeah. So therefore, you see the VL, I mean, I'm writing from this equation. So it is 600. So 600 times 10 to the power 6. I just converted into volt ampere.
Yeah, I forgot the mega. That's my mistake. I'm sorry. Thank you.
Okay, then root 3 and 160 multiplied by 10 to the power 3. So therefore, automatically this 10 to the power 3, 10 to the power 3, it is cancelled. So here it is 10 to the power 3. And then you cancel 1010. So ultimately your 60,000 over this one. So then you should be getting 2.17 kV. Yes, that one.
Thank you. Thank you, Dr. Ali.
Okay. So Venkat, did you get this one? Venkat, Sindhuja, did you get this one?
I got it, Dr. Ali. 4.330 kilovolt.
So 4.33 kV?
Yes.
Okay. Venkat, did you get properly? The motor terminal voltage? I mean, you can say this is VT. If I use VL here, then you can use the symbol VT here, 4.33 kV. This should be the answer. Venkat, are you calculating still?
Yeah, yes, sir.
Oh, so still it did not give you the correct result?
Uh,
Did you see what I did here? Yeah.
yeah, yes, sir. I was in.
Okay. Just to do this calculation, then you should be getting the same result. Venkat, did you get
Yeah,
it?
yeah. Now I got it.
Okay,
I
okay.
got
Thank you.
4.32. Is it fine?
Okay, I mean
Yeah,
approximately.
just a point.
Yeah, okay, okay. Okay, so then this is fine. So I am going back there. Okay, so therefore everybody got this one. Now moving forward, we have 10 more minutes, so we can cover something. Everybody see there are a couple of questions here. Like you will be facing similar questions in the exam. Read this one. In the following automatic voltage regulator, which is that AVR, and then governor, which is this one, control system models, what is the significance of symbol T? So therefore look this diagram, like before I think previous class I discussed about this one. This is the AVR model. So which produces the field voltage by controlling the terminal voltage. But here there is like low pass filter, there is T, capital T. And then same thing in the governor model, it produces required mechanical power by controlling the speed of the system. And in this model also there is capital T. So that's the question. What is the significance of that symbol T in both cases? What is T?
So it will cause the time delay of the control signal.
Yes, so that is basically the time constant. So that is right. So this T is the time constant. And time constant is nothing but the representation of some delay. So therefore, when it is asking significance of symbol T, you will be telling that in both AVR and governor models, T represents the time constant. S is the Laplace operator S, and T is the time constant, and time constant definitely represents a time delay. That is
So K is the
the gain.
constant.
T is the gain.
Gain, yeah. Yes,
Yeah.
sir.
K gain in this case, just I use different symbol. G is the gain.
Yes.
So basically, this is the PI controller. Doctor, right, doctor?
The low pass filter.
Yes, yes, yes.
Yeah, low pass.
So the goal is that, for example, if you see the first on AVR model, the voltage difference and the output of this one, it will be like a pure signal. There should not be any oscillation. That is the function of the low pass filter. For example, in an electronic circuit, you are looking some output, but that output has some oscillation. And then if you use this one, and if you take the output, that will be ripple free. You will not see any oscillation. That's why in real practice, a low pass filter is used. Yeah. These are the like real signal, real analog signal. So immediately pass through a low pass filter so that you get pure signal. And then from the top, you see EFD0 that is coming, that is the pure DC. So it's constant. That's why to make it purify, to make it ripple free, this low pass filter is used. So therefore, I mean, simply speaking, the T means the time constant, and definitely like Manoj is right, that represents the time delay. So everybody, could you follow me?
Yes, Dr. Ali.
Okay, everybody, are you writing down the answer in your note?
Yes, Dr.
Yes. So therefore, at the beginning, Manoj, when I say you may expect 7 to 8 questions, I mean, maybe the answer will be simply like this, one of the question. Yeah.
Okay.
So therefore, it is not my intention that it will take 3 hours. Just to make sure that all of you are starting at least 30 minutes ahead or 15 minutes ahead, and then you take time to scan and make the PDF, and then upload a single PDF file only. That is the goal of 3 hours. Yeah. Okay, so everybody, read the question number 2. Suppose a synchronous generator is facing the issues of frequency variation. Would you control AVR system or governor system to fix that? Explain your answer. So therefore, everybody once again understand the question. Now, see, synchronous generator may face various problems. In this case, I said it is frequency variation. You might see that, okay, its voltage is fluctuating. That is another type of variation. You might see that its speed is fluctuating. You might see that active output power is fluctuating. So there can be varieties of issues. But here I am specifically saying, suppose you have a synchronous generator that is facing the problem of frequency variation. Its frequency is changing. So that's the problem. So, and it is the expectation that with the help of this AVR system or governor system, you can fix that issue. So the question is, which one would you choose? Would you choose figure 1 or figure 2? That is
I
the main.
choose
Sorry?
Governor.
The governor.
Governor, yes.
Governor.
So why? Why governor?
Because it controls the speed. I mean,
Yeah, using
type.
the excitation control.
Yeah.
No, excitation control is this one, AVR.
No, if we see the figure 2, then there is a
Yes,
speed omega m and omega m. No?
exactly. So therefore, is speed, and then you see the last product, final product is the mechanical power. Yeah.
So yeah.
Yeah.
So active power means active frequency control.
Frequency control. Therefore, if you see that NS on 20 F over P, that is speed is related to the frequency NS on 20 F over P. Pole number is fixed in a machine, but the frequency and speed changes. So therefore, this means that you have to use governor, because frequency variation means if you control the speed, then the power will be fixed, power will be controlled, and that will fix the frequency. So therefore, what is Venkat? Like you are just mentioning the excitation.
Yes.
Excitation.
I made a mistake.
Yeah. No, you are fully fine. I'm just clarifying. So if you control the excitation, meaning that you are controlling, that can control the voltage.
Yeah, voltage. Yeah.
Yeah.
Yes, sir.
Right. I think everybody understood, right? This the
Yes,
answer
sir.
to question number 3. Sindhuja, can you follow me?
Yes, Dr.
Okay, please note down in your paper.
Yeah, I'm doing.
Yeah, you will be faced this type of critical question. Yeah, so that might take the 3 hours. That is a different thing. Yeah, those type of critical thing. Yeah. Okay, everybody go question number 3. I think we can just discuss these two and we can close today. An aircraft electrical system operates on higher frequency, 400 hertz or even higher. I mean, this is in real situation. The aircraft or aeroplane that has a power system and it operates at higher frequency. And can you see the frequency 400 hertz? Or even it could be much higher than that. Now, in case of a fault in the electrical power network, now aeroplane has also, you can say it's a microgrid, a small system, microgrid system that has a power network and some fault happened. So will the active power control or reactive power control help maintain stability? Now, for example, unfortunately, some fault happened, either short circuit or open circuit, something happened. And then definitely the fault impact will go on the shaft system, definitely. So will the active power control or reactive power control help maintain stability? The
Both
question,
of them.
both of them, but is there any dominating? Which one could be more dominating, active power or reactive power control?
Since they mentioned about the frequency, it might be the active control.
Okay, yeah, so that is right answer. So definitely n equal to 120 f over p according to that equation. But then I would equally prioritize.
Oh, okay.
Equally, both the reason is that you see the reactive power. So reactive, then let me for a moment take you on the board, so that will make much more clear to you. Hold on. So why I am saying that on reactive power as well, that in that electrical aircraft system, the cable that has these things, right? So the cable has R and L. Now, you see the current is flowing, whatever the amount of current is. But then this is resistance, this is fine. How about this one? So therefore, I square XL. So there is some power loss here as well, which is reactive power. And everybody see, what is XL? XL means omega L. And what is omega L? Omega means 2 pi FL. So therefore, what is the frequency? 400. So therefore, when there will be any disturbance, definitely the shaft speed will increase and that will increase the frequency much more. Consequently, your QL, inductive reactive power, will be much more. So there will be much more loss in the system. There will be some power factor issue as well. Power factor will be low lagging because of this thing. So that's why you have to take care of the reactive power as well. So this means the appropriate answer would be you have to control both active power and reactive power. Because active power control means frequency, that is fine. But you see, if you analyze the inherent situation, then the mathematics is telling you that it is related to frequency, that reactive power consumption. So meaning that because there will be huge reactive power loss, you have to handle the reactive power as well. So therefore both control are needed. So everybody, could you follow me what I said?
Yes, sir.
You see that the frequency has impact on the XL, omega L. That's why that is important. Okay, I think there's one more question and then we can conclude for today. Consider in a large power network consisting of 50 generators, it is desired to install few control devices at some generator terminals with a view to maintaining the transient stability of the network. Is there any approach except optimization techniques to find out those locations? explain your answer. So meaning that you have a huge network, and that network, power network, has 50 generators at a scattered place. And now what is your goal? It is desired to install few control device at some generator terminals. Now the thing is that you can place 50 device, for example, 50 control device, whatever it is, reactive compensator or active power compensator. Definitely you can put 50 control device at the terminal of 50 generators. But you will not do that. Power engineers do not prefer that because it will incur cost. It will increase the cost huge. That's why you have to make some sort of optimization. That is the goal of any optimization technique. So with the help of optimization technique, you can figure it out some specific location. For example, out of 50, maybe 10 location or maybe 15 location. That if you put control means at those 15 location or 10 location only, then still the system transient stability can be maintained. So now optimization means definitely you all know the genetic algorithm, or there are other particle swarm optimization, tapu search algorithm, and we colony. There are lots of optimization technique. Definitely you can. But what I am asking that is there any approach, any method except optimization technique or other than the optimization technique that can help you figure it out, reduced number of location?
Coherency, maybe.
Coherency, right. So you see that other day, I think 2-3 classes back, I was mentioning the concept of coherency. Concept of coherency means you will be looking the torque angle or rotor angle of those generators, how they behave, and then you can figure it out. You can cluster them, you can group them, maybe 10 group only, and add those 10 for those 10 generators, sorry, for 5 generators or for each 6 generator, you put on control device. In that way, you can reduce the number of control devices and you can reduce the cost. So therefore, everybody write down the answer would be, yes, there is approach, the concept of coherency. If we can calculate the number of coherent groups in the system, then we can choose those coherent group locations to put the control devices so that it maintain the transient stability and simultaneously your system or installation cost or operational cost get reduced. That is the answer. Could you follow me, everybody?
Yes, Dr. Ali.
Yes, sir.
Okay, everybody, have you note down the answer to your note?
Yes, Dr. Ali.
Okay. Okay, so with that, I think already 7. So I like to conclude here for today. Then I will be, and then I will be returning your graded homework definitely by Thursday, or even much before, by tomorrow even you can know. And then I will be discussing the answers for those questions as well on Thursday, the homework number 1. Okay, so with that, I'm stop.